Okay, so just a thing, this is the last thing for the quiz on Thursday. Thursday's quiz.
Yeah.
No corrections, no retakes for this one. Sorry. Welcome to college level classes. Some of you should be used to that. Um, but this quiz is not terribly difficult. Might be the easiest one of the year. So this is the last thing. This is direct and inverse variation. Direct variation looks like this. The two variables I'm going between are y and m, and k is an unknown constant, or m is an unknown constant in this. My two variables are y and x. That's what I'm trying to say. And m is an unknown constant. Usually most books label it kx. Doesn't really matter. But this is called the constant of proportionality. These show up a lot in science. Those of you that have any interest in engineering, even probably medical, that this is constant of proportionality. It's really actually not hard. Most of them are stored on your Inspire, most of the really common ones. um, Otherwise, you know, you might have to memorize a couple for a college class somewhere along the line. Memorize four for this test and four for that test, and they're not that bad. But if you're a professional or solving random problems and you don't know it, you Google it. It's they're pretty simple to come up with. For different things, though, a lot of times with real data, we'll have to take the data and go find the constant of proportionality. Direct variation, which is what we're starting with, means as x increases or my independent variable increases, my y also increases. My inverse variation will mean as x increases, y decreases. They call this the gradient of proportionality, aka the slope. Um, Same thing. Making connections, Charles' law, Boyle's law, several. Charles' law, I think, is the one that is direct. Boyle's law and Gay-Lussac law, several of the gas laws that you hopefully learned in chemistry are um, direct or inverse variation. So here, the volume of a sample of nitrogen is directly proportional to the temperature. The volume of the sample of nitrogen is 600 milliliters at 300 Kelvin and becomes 700 milliliters at 350 Kelvin. Find a formula that describes this. So, one of the keys here is the temperature is in Kelvin. Okay. That means volume theoretically is zero when you are 0 Kelvin. You have to have an absolute temperature scale where 0 degrees is zero temperature. There are no negatives. So find a formula that describes V as a function of T. So they didn't tell us this, but volume varies directly with temperature. V equals KT. So 600 equals K times 300. K equals 2, correct? And that works with 700 and 350. Use the formula to find the volume when the sample temperature is 400 Kelvin. So my formula is essentially V equals 2T. 2 times 400 is 800. Okay, as an nth power. So here we've got A equals pi r squared. Again, this is varies directly with a power, r squared. My constant of proportionality is pi. So the distance in meters a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. After 1 second from the release, the ball is at 0.9 meters. So distance is directly proportional to time roll. Okay, so D equals KT squared. That's my equation for A. How far? So, oh no, I'm supposed to solve for this. 0.9 equals dk times 1 squared. Yep, so k equals 0.9. My equation, my specific variation equation is this. I've solved for k using the instance they gave me here. 1 is the time, 0.9 is the distance. How far will it be after 4 seconds? And that is 16 times 0.9. I'm not sure offhand. $14.4. If I look at the answer key, it does the calculation for me. It's amazing. So that is direct variation. Pretty straightforward. Pretty algebra 1, actually. Enjoy your direct variation problems. Inverse variation is the same thing, but with division. As y or as x increases here, y decreases. So direct variation looked like a line, inverse looks like a rational function. So on a balanced lever seesaw, everybody's probably played with one of these as a kid. The weight varies inversely with the distance of the object from the fulcrum. If Matthew is 140 pounds and is sitting 7 feet from the fulcrum, where should his brother, who weighs 98 feet, sit to balance the seesaw? So weight varies inversely with distance. You can use M or K, I don't care. 140 equals K over 7. Oh, no, the distance, the weight, yeah, that works. Guess it works either way. To solve this, I'll do 140 times 7. It's 980. So my equation is W equals 980 times distance. I guess I didn't set this up in the easiest way, but to solve, I'll multiply both sides by D and divide by 98. D equals 10. So his brother should sit 10 feet away. Okay. That section was not too tough. Modeling with cubic functions. Again, this is going to be a lot like the quadratic ones, but cubics. Okay. This is the box problem. Some of you have never seen the box problem. But the box problem involves taking a flat sheet of paper or a flat sheet of cardboard, ultimately, cutting out these little corners that are X by X, folding it up. If this doesn't make sense, ask. I can make a model. and the sides fold up and you get an open top box. You tape the side corners together right here. And you get explain why the length of the box is 30 minus 2x. Well, I'm got 30 here. I'm subtracting 1x here and 1x here because the box is really inside this dashed part. And the width thus is 15 minus 2x. Then says write a function that models the volume. Well, volume is length times width. The height of the box, when I fold it up, this dimension here is x. So this is my model for the volume of the box. I don't need to do anything further with that. Now it says find the values for which x is meaningful. I'm going to erase some of my drawings on the box, but I want my volume function somewhere. I guess I should have wrote it off to the side. I'm going to scroll up a little bit more, and I'll just. So here's my volume function again. So the values for which this is meaningful, neither length nor width can be negative. Meaning 15 minus 2x, I'm choosing this one because this is going to have the smaller value, has to be greater than or equal to 0. Really, actually, it shouldn't even be no or equal. It can't be a 0 width. That's not a box. So when I solve that, I get x is greater than, no, x is, yeah, greater than 7.5. No, it should be x is less than. Oh, I'm going to divide by a negative. X is less than 7.5. It's like, how is this not the way I think it should be? And x obviously has to be greater than 0. Otherwise, again, you have a flat sheet of cardboard. Plot and graph the function and find the maximum point. So now is where we need to go to the calculator. And graph that. And I'm just going to do a scratch pad. And I remember my equation well enough to graph it. Oops. And I'm going to show the whole cubic for a second. And then we'll talk about what it actually means. So negative 10. I think I need to go up to about 20. I'm guessing at 500, 500. That wasn't big enough. Looks like they're close. Usually I go, yeah, usually I go double, but I don't think I needed to there. So that's a cubic. Unfortunately, this whole thing is not meaningful because down here, this would be negative volume. It also corresponds to me having negative side lengths. So it is down here. So I'm going to make the window actually be meaningful by going back to my calculator. We said x had to be between 0 and 7.5. I really didn't need the negative part. But here's my graph. This is the meaningful part of my graph. Notice the volume is 0 on both ends. And it wants me to find the maximum. Menu, analyze graph. Maximum. That's a little hard to read. So x is 3.17. The maximum volume is 650. So here, you work to design a department. You work in the design department for a soft drink company. You're experimenting with a new cylindrical container for beverages that is slightly narrower and taller than the standard container. For your experimental container H, the height of the container is measured in centimeters to be 5 times larger than the radius of the base, also measured in centimeters. So height is 5 times larger, it says. Okay, so find a formula that describes the volume. Well, volume of a cylinder in general is pi r squared h. But we also know that h equals 5r. Or when I simplify, 5 pi r cubed. Find the volume when r is 3. Three cubed is 27. 27 times 5 is 135. The volume of the container is to be 400 cubic centimeters. Explain why 80 equals pi r cubed. Well, that's pretty easy, actually. So this is my formula. I divide by 5 and I get 80. My explanation is me showing my work. Fitting data with a cubic model. Okay, this is just going to be a regression, except, oops. Instead of doing, we're going to save time and I'm not going to actually have you do this. You're going to enter this on the calculator and you're going to choose cubic model. So if I'm in here, menu, statistics, stat calculations, cubic regression. You're like, oh, okay. Same thing you've been doing, but with a new function. Now we're going to talk about doing it with exponential functions. Exponential growth or decay. A couple of things here. This is your basic exponential form. If x is positive, I'll write that as x is greater than 0. Growth involves values for b greater than 1. Decay, oops, involves values for b between 0 and 1. If, however, x is negative, I'll write that as x is less than 0. You swap these. So form an equation to model this. So Hugo deposits $900 into account with 4.5% interest annually. That is, so per annum means just the interest rate. The annual interest rate compounded per month. If you do it the monthly interest rate, it's actually just this. So your general formula looks like this. And we talked about that at some point. If they want the monthly interest rate, it's just the R over N. But the formula for this, 900, why did I write equals? That's times. Suppose I should write A of R of T or something like that. A of T, that's now a function. It's 900, 1 plus 0.0455 over 12 to the 12t. Why can it be described as exponential growth? Well, it's in the form AB to the x. B is just this little more complicated thing. And there's a transformation 12x. Calculate the money to the nearest cent Hugo has in the bank after 10 years. I don't know why I'm doing it this way. I can't write. A of 10 equals 900 1 plus 0.0455 over 12 to the 12 times 10. And Izzy's getting the answer for me here, hopefully. 1,417.74. 34. And it does say to the nearest cent. So we do need to do not go past a cent ever. The last one here, it says, how long will it be for Hugo has 3,500 in his account? I just set the equation equal to 3,500 with an unknown t. I'm going to set it equal to 0. And I'm going to show this because of when I show my graphing, so I'm going to solve this by graphing because I don't feel like solving it by logarithms. Figured you would all be on board with, hey, let's solve this by graphing. But I need to show this equation. And then you could say from here, graph to solve, show the graph, make a quick sketch. Okay, I remember my equation. I'm going to clear that because I can't see what I'm doing. Oh. Um, 900, 1 plus 0.045. That's in the way. You do have to do it as x. Oh, there's an extra 5. Okay, thanks. 0.455. And yeah, I think the problem is here, we did not, it's going to take more than 10 years. We were only 1,400 years. So I didn't change my window. We're 1400 after 10 years, so I would expect, oops, wasn't what I wanted. I would expect to be probably less than 100. I don't really care about my Y's on this. I need to find my zero. Looks like 29.9 years, so 29 years and 10 month, 11 months. You'll get there. So not very quickly, but $900 did turn into 3,500. That's probably better than inflation. Um, okay. The market value for a certain model of Volkswagen Golf is recorded for the first 5 years. The first 5 years can be modeled by this equation. What is the value of the car when it is purchased for the first time? Well, you can plug in zero for X here. B of zero. And so it's just this value. It costs, this is in dollars. Yes, US dollars. I guess I don't know how much it costs, but that's the value. According to the model, it is expected the value of the Volkswagen Golf when it is 3.5 years old. So plug in 3.5.
B is 4,829.
Okay, so this one, again, I'm going to use X. I'm going to solve by graphing. I'm going to actually do this because I want to discuss if it says this model is good for 5 years. I'm not sure that this is going to be within 5 years. I'll clean off my graph with triple clear and I'll get rid of that. It was 20,350, right?
Uh,
Okay. To the, well, it wasn't to the X, it's to the negative X. And then I want it when it's equal to 5,000. That gives me my graph. 10.6 years. That's not within the reason it said the model was for. So we honestly can't define this. If this model continues, that'd be 11 years. It does say in complete years. So we're looking for 11 years. But up here it says recorded for the first five. Oh, so they recorded it and made the model after 5 years. So I guess this could be considered valid. Maybe, maybe not. You're extrapolating, but it's probably within the realm of reasonable. So, exam tip in real life, vast numbers of variables affect the price of a car. First, just distance driven, number of car owners. It's not just year. Every model is subject to some criticism. Remember that the creation of a model requires balancing act between efficiency and accuracy. The purpose of the model will determine how accurate it needs to be. Now, if you go and you look up your car's value on Kelley Blue Book, they have a much more complicated equation because they factor in more variables than years. Okay. So radioactive material, M, is modeled according to this function. It is determined that after 20 years, the amount of radioactive material present is 50. So that allows me to get the value for K. E here is the number E. It is not a variable. E will never be a variable anymore. So 50 equals 250 e to the negative 20, or negative k times negative 20k. It's k times 20. I'm just going to write it in the way we would normally write this. I'm going to solve this by hand, sort of. I will convert to logarithmic form, and then I'll divide by negative 20. And I get the value k equals, the equation shows me it decays exponentially because e to the negative k. The initial amount of present, I guess I'm doing C. I'm doing part C. The initial amount present, I'd plug in 0. Be careful to actually plug in 0. That went wrong for some people on the test. But usually with these exponentials, that's the initial amount. Sometimes there's a plus. For Izzy, what'd you get for K when you plugged that into the calculator?
8, 0.
And that is 3 sig figs, 0.0805. How much material would be left after 80 years to 3 decimal places? 250 e to the negative 0.0805 times 80. And we just plug that into the calculator. Okay, in the interest of time, I'm going to trust that you guys are capable of plugging that into your calculator. Example 4 says to triple his money. This is back to example 1. You just do the same thing we did for 3,500, but with 2,700, tripling his money. Okay. Same ideas. Fitting a model, you just choose exponential. I believe exponential usually does have it as e to the kt. Let me look for sure. There might be a couple options here. Menu. Oh, wait, it's not going to be here. You'd have to enter your data. Show. It does just have exponential. Yeah. Okay, modeling with sinusoidal functions. This is going to be the new one. Sine functions make a wave. Okay, we've got y equals a sine bx plus d. A being the vertical stretch on the wave. That being A, also known as the amplitude. We're not doing any phase shifts. D is the center line or principal axis is what they're going to call it in IB. That's probably the more technical name than midline or center line. The period of this wave period by default is equal to 2 pi divided by b. Okay. We will be working in radians. The key to radians is that 2 pi equals 360. 2 pi being the circumference of a circle of radius 1, and it equals 360 degrees. I'll define radians a little bit more thoroughly afterwards. So these are a couple of important things for graphing trig functions. We're not actually going to graph any by hand, right, today. So here we've got a couple of different functions. They are both sine functions, which means they cross the y-axis on their principal axis or right in the middle. Okay. And I'm going to open this and show a little bit of playing around with it. So both of these, again, being sine functions. I can move my principal axis. My middle still stays where it is. Adjusting b. As b gets larger, since the period was 2 pi divided by b, larger values of b make smaller waves. We're not really going to deal with any negative values of b. Adjusting the amplitude. If the amplitude becomes negative, it just flips it upside down. So really important to note that, oh, they're doing them in, interesting. They're doing this in degrees. I never graph in degrees. I think it's a little crazy. But if you are, I'll show you how to adjust the calculator for that. So here's my sinusoidal function where x is degrees. Find the amplitude and period and principal axis. Well, I don't even need to bother graphing by hand. Amplitude. 3. Are they going to call this -3? They're probably calling it -3. Nope, they're just amplitude is positive. Amplitude's always positive. Okay, amplitude is 3. It's like, that's what I want to call it. The period, my b here is 2. So 2 pi over, no, 2 times 3. Oh, 2. Okay, period is 2 pi over b or 360 over b. So b here is 2. They want this in degrees. 360 over 2 is 180. Principal axis. Just the d value, -1. So the trig part isn't really that significant here. It's mostly the transformations that you've done lots of times. The cosine works exactly the same, except I'm going to show, I guess I want to open this and show one thing. As I go through the axis, they're not doing any horizontal shifts right now. I'm going through either at the top or as I adjust the A, it might, as the A becomes negative, it's going to flip it to the bottom. Okay. So the sine goes through the principal axis on the y-axis, unless of course there's a horizontal shift, but we're not dealing with those. The cosine goes through the top or bottom. And usually when I graph these, I actually they've dashed the principal axis here. I usually dash the top and bottom line too. This helps me draw them in. And that is just principal axis plus and minus amplitude. So consider this function. It says find its amplitude. Amplitude is, period we'll do last. Amplitude is 4. Period 360 over, that's x over 5. B is 1/5. 5 times 360 is 1800. And those are my values. Okay. The graph is shown below. Determine the numerical values. So it does not show me A or B. But I can tell that the period is here. I'm going from 2 to -6. So, oh, they did show that. The amplitude is 4. It starts up. So this is 4 cosine. Period is 90. And that's 360 over B. B is 4. They're both 4. Wasn't really expecting that. Final thing, an application. It's a pretty basic application. A Ferris wheel with radius 25 meters is rotating at a rate of 3 revolutions per minute. So the period for one revolution, if it's doing 3 revolutions, is 20 seconds. It does say to be relative to time in seconds, so that's good to know. When t equals 0, the cabin starts at the lowest point, which is 5 meters above the ground. Write a model for the height of the cabin as a function of time. So it starts at the bottom at 5. The center is 30. And the top, since the radius is 5, should be 55. It should be back down at 20 seconds. This is 0. So this is a negative cosine. It has an amplitude here of 25. So this is going to be -25. It's a cosine because it started down and it started negative cosine because it started down. Period 20. For today, we're going to go 360 over B. So that's 20B equals 360. I will divide both sides by 20. B gives 360 over 20, which is 18. Plus 30. And let's double check the answer, but I believe that is correct. Yep. And I think sketching it out made it easier for me. I guess my 30 is not very nice. But for the most part, these you're just having to identify those parts of the transformations. There'll be a couple of word problems, but most of the rest of the things will be modeling exponentials, cubic, quadratics, linear. Okay, that is it for today.